Welcome to this video on sampling distributions. By the end of this video, you should be able to distinguish between a parameter and a statistic, create a sampling distribution using all possible samples from a small population, and determine if a statistic is an unbiased estimator of a population parameter. All right, so our scenario today is talking about the Chapter 6 test. How did it go? So what we're going to do is we will be taking a sample from a population and we will use the average from the sample to estimate the average for the population. So first, I'm going to say there's only 4 people in my 5th hour class, and these were their test scores on the Unit 6 test. All right, so to make a dot plot, hopefully you remember how to do that. Go ahead and make the dot plot and take a sample of any 2 scores and find their average and come back to the video. All right, so here is my dot plot, and we're going to title this the population distribution of scores. This is all the population of my 5th period class and their scores. Okay, so it's the world's most boring dot plot. And then I said just select any 2 of the scores and find their average. I chose 60 and 70. So they had a mean of 65. And I just want you to remember that X bar means this is a sample mean. Okay, so now the next part, what I want you to do is I want you to go find all the possible combinations of a sample size of 2. So I did 60 and 70, then also do 60 and 80, 60 and 90. Get all the possible combinations of 2 and find their averages here. Then you're going to take these numbers and you're going to make a dot plot of their distribution for that. And then we'll come back together. All right, so when I came up with all of my averages of any sample size 2, I brought them and I put them on the dot plot. And the name of this dot plot is this is a sampling distribution, and we were putting on there the sample means, so of X bar. Okay, so here I have my distribution, and I want to remind you we need to be able to identify what an individual point means. So in this case, that dot is one sample of size 2 with a mean of 85. So if we talked about that one, that'd be one sample of a size 2 with a mean of 80. You need to be able to identify what each dot represents. Okay, and so this is our sampling distribution of so this is of the samples. This is the actual population here. So up here, that one dot is one individual that has of 90. All right, so in this, the dot plot, each dot represents one person's test score. And down here, we took samples to create these numbers. So each dot represents a sample of size 2, and in this case, it's a mean of 85. All right, so let's take a second. What is the mean of the population? Okay, so if I take my test scores and I add them together, and I divide by 4, I got a mean of 75. Okay, so up here when we were talking about our samples, we used X bar. I want to remind you that you want to use mu here because I'm talking about the population, because that's the population mean. And that anytime you're talking about the population, that number is a parameter. But if you're talking about samples, the numbers are called statistics. Okay, so a parameter is a population and a statistic refers to your sample. All right, so we got a population mean of 75. So that's right here. Here's my population mean. Well, it also is the mean of my distribution. The distribution mean is also 75. So what that means is my population and my distribution had the same mean. That means my statistic was an unbiased estimator. Because the mean of my sampling distribution equaled my parameter. So remember from before, unbiased means there's no systematic pulling to one direction. So in this case, here's my mean and I've got numbers on both sides and it's symmetrical. That's how I know it's unbiased and that my mean is the same as the population. Because in the real world, often we don't know what the population mean is. And so if we have an unbiased estimator, such as we took good random samples to get our data, and we take a lot of samples, the sample of that distribution, of that sampling distribution, we can then say is the same as the population because it should be an unbiased estimator. All right, so let's summarize this down. Let's flip this over. All right, there's 3 items that I want to summarize down for you on the back, and they take about the same amount of space each. The first is that I want you to remember that a parameter is a number that describes a population, and that a statistic is a number that describes a sample. So when we use parameters and statistics, and we're going to write their numbers down, we need to remember their notations because the way we write the notation is important and it conveys information to a reader that this is a parameter or a statistic so they understand where the number is coming from. So when we're talking about mean, we just talked about this. The parameter is mu. You'll say mu equals, and the statistic would be x bar equals. So we've already talked about that last semester. We also talked about standard deviation last semester. For the parameter, if we're talking about the population, you want to use the baby sigma, the lowercase sigma, to equal your standard deviation. Okay, and then for a statistic, if it's coming from a sample, we'll use the S. And in our calculator, I'll say SX. That means that's a sample standard deviation. The one we have not talked about is proportion. Okay, so a proportion, if I'm talking about the population, I'm going to say P equals a number. Okay, if I'm talking about a statistic that my number came from a sample, I'm going to say P hat, similar to our Y hat when we were doing our linear regression, P hat. So these are important that you use them appropriately and consistently throughout your work. All right, and the next thing is your sampling distribution. All right, then we had our sampling distribution, which shows the statistic found in all possible samples of a particular size. We did of size 2. Okay, so in the real world, it's not really possible to have all possible samples represented. If I had 400 test scores and I wanted to have all the possible sample size 2, that would take forever. And so in the real world, we tend to take much less. And so it's not actually a sampling distribution, but we'll still call it a sampling distribution. Okay. And so what we would have our distribution and we would title it, it's a sample distribution of the statistic, whatever it is. So sampling distribution of the statistic. And that statistic could either be X bar or P hat for our purposes in AP Stats. Okay, you could also do standard deviation, but it'd be one of these 3 things really is what we would be talking about for the most part. And remember, an individual point will represent one sample. and it's the statistic from one sample. Okay? And then the last thing that I wanted to remind you of, we can say a statistic is an unbiased estimator if the mean of the sampling distribution that we would draw here, if we take a bunch of samples and graph those, if the mean of this distribution is equal to that of the parameter. So on the front, our sampling distribution had the same mean as our distribution of test scores. Okay, that's when you know it's unbiased because it hasn't been pulled off in one direction or the other. And another important thing to remember is when you increase your sample size, the sampling distribution variability decreases. We only had a sample size of 2. Now we didn't have a large population that we were pulling from, but a larger sample size will reduce your variability. All right, what I'd like you to do is try this, check your understanding, and come back and check your answers at the end. This is good practice to do on your own. All right, so our scenario is the James family has 5 children, Jocelyn, Elise, Michael, Erica, and Sarah. And we wanted to complete a table of all the possible samples of size 2 and their averages. So here I've got all our possible samples of size 2 and their averages, and then I created a sampling distribution of those averages here. To find the mean of the sampling distribution was 12.8 when I added all these numbers up, divided by 10, and the mean of the children's age was also 12.8. So because these numbers are the same, my sample mean is an unbiased estimator of the population. Okay, because they're the same, I know I had an unbiased estimator for the population. And then what if we had taken a sample of size 3 instead of size 2? Would the variability of the sampling distribution of the sample mean be larger, smaller, or about the same? And then I ask you to justify your answer. Well, it would be smaller because when you increase the sample size, you decrease the variability of the sampling distribution. Hopefully this was helpful. Let me know if you have any questions. See you in class.